Okay, good evening students. So today we are going to see about fiber numerical aperture measurement. So before getting into this topic, so what are the important, okay. So first of all, we should know the definition. Okay. So definition for numerical aperture and formulas, then followed by block diagrams, then explanation. Okay, so these are the four things we are going to see about numerical aperture measurement. So first of all, definition. So numerical aperture is nothing but a light gathering capacity of an fiber. Okay, so this is what the definition. It's nothing but a ability of a fiber or a capacity of a fiber to gather the light which is focused into the fiber. For example, this is the fiber where you are going to send a light. It's going to form a zigzag. Okay, in case of single mode step index. Okay, so this is the propagation of light in single mode step index fiber. So the light gathering capacity of a fiber is simply called as a numerical aperture. So which is the definition. So here the numerical aperture is one of the important optical fiber parameter, okay, such as light gathering efficiency, as I told you earlier, light gathering efficiency or capacity. And with this Na, you can find the normalized frequency V. So Na can be used to find the normalized frequency V, which we have seen in our first unit. Okay, so here there are two sort of fibers are there. One is step index and another one is graded index. So in case of step index fiber, okay, the numerical aperture for a step index fiber is explained as numerical aperture which is equivalent to sine of theta a, which is nothing but n1 square minus n2 square whole to the power of 1 by 2, which can be written as n1 square minus n2 square. So where in that case of n1 is nothing but Ri of core, then in case of n2 which is Ri of cladding. Okay, so this is the numerical aperture formula for a step index fiber. Okay, it may be a single mode or multi-mode, but the radiation profile should be in a form of step index. Okay, now the theta a, which is nothing but the maximum acceptance angle. Okay, so you can find Na using acceptance angle. Na can be used to find acceptance angle, or with Na you can find acceptance angle, or with acceptance angle you can find Na. Okay, so as I told earlier, where n1 and n2 are the refractive index of core and cladding. Okay, so in case of graded, so this is case 2. So case 1 is step index. Now we are moving to case 2, the graded index profile. So as you all know that the graded index fiber which has a variable refractive index from core to cladding. So in case due to that, instead of zigzag, the light used to bend at every micrometer of a radius, so it may go like this. Okay, So this is the propagation of light in a graded index fiber. So the Ri, which is changes with respect to radius. Okay, so that's why the numerical aperture for graded index Na for Gi fiber, it can be given as with respect to radius, because at center of a core the n1 value will be high. For example, if it is 1.48, then n2 is cladding, which is 1.44. So every micrometer of radius which moves from center to cladding, it will have a variable value. That's why here the refractive index of core, it will be in a function of radius. That's why they are representing n1 especially as function of r, where n2 is always constant. So this is what the refractive index of graded index fiber through which you are calculating Na. So now we are going to calculate the numerical aperture by two methods. One is rotating stage, another one is trigonometry method. So this is the stage 1. So this block diagram is having a weightage of around 4 marks. So here you should have a fiber. Okay, so this is similar to the experiment which we have performed in our laboratory. So this is a fiber, it carries information in a form of light. Now this is the screen. Okay, so followed by the screen there will be an photo detector. As you all know that when a light falls in a photo detector, a light falls into a photo detector, it will be converted into electricity, right? It will be converted into a current. So in this setup, as you could see that the fiber may have a length of 2 meter long. Okay, then the end of a fiber will be prepared by end phase preparation. So which is nothing but the end will be cutted, smoothed and polished and cleaned with the cleaning solution. So the fiber is prepared like that. The length of a fiber may be 2 meter. Then this is a rotating stage. You can rotate in clockwise and anti-clockwise. When you rotate the stage where your fiber is folded or mounted, so based on that the intensity falls into the photo detector may vary. If it is in the same line of axis, there will be more amount of energy or photon falls on the surface and it gets converted into signal. If you increase or decrease an angle, so there will be a change in the received intensity by which you can measure a numerical aperture of an fiber. This is one method. So here, as I told earlier, they will be using 2 meter length of GI fiber. So its phases are prepared and they will be using 0.85 micrometer, which is nothing but 850 nanometer. So passed in all possible angles and you will having the reading by which you can find the numerical aperture. So this is one method. Then so by this you can find the numerical aperture, which is nothing but our equation 1. Then you can find numerical aperture by another method which is called as trigonometry method. Okay, so the trigonometry method is nothing but a mathematical method. See here, it is like a triangle. Okay, so it is like a triangle here. So you could see A and this is D. So the same method which we are used in our laboratory to find Na using glass stage, right? So the same, the distance between the screen and the fiber, which is denoted as D, where the entire area of illumination is represented as a A. So by this method also you can find the numerical aperture. So here you could see the formula, so which is very important. This is an important formula. Okay, so where you could see A is an area of intensity, where D is nothing but a distance between the fiber and the screen. So by which you can find the numerical aperture. Okay, so by these two methods you can find the numerical aperture. So either equation 1, which is nothing but our step index, equation 2 is nothing but our graded index, by which you can find the numerical aperture. Thank you.